In this session, we will discuss about a Nyquist stability criteria. That is a continuation from the previous session. Actually, this session will explain about the basic Nyquist stability criteria. See, suppose we have a closed loop transfer function C of s divided by R of s is equal to G of s divided by 1 plus G of s into H of s. That we are familiar with this equation. And the characteristic of the equation of the system is given by, we know that 1 plus G of s into H of s equal to 0. And here we are making a substitution that 1 plus G of s into H of s is equal to F of s. So actually in the Nyquist stability criteria we are discussing, we will make a mapping between F of s and G of s into H of s quantity. So we are taking two quantities, F of s and 1 plus G of s into F of s and G of s and into H of s. So first we can write G of s into H of s in terms of two polynomials, that is k into s plus z1, s plus z2, etc. up to s plus zm divided by s plus p1, s plus p2, etc. up to s plus pn, where m is very less than n. So z1, z2, etc. up to zm are the zeros and p1, p2, etc. up to pn are the poles. And we can write f of s as f of s is equal to 1 plus G of s into H of s. So that will be equal to, we can add 1 to the quantity k into s plus z1 into s plus z2, etc. up to s plus zm divided by s plus p1 into s plus p2, etc. up to s plus pn. So we can finally get f of s is equal to s plus z1 dash into s plus z2 dash, etc. up to s plus zn dash divided by s plus p1 into s plus p2 into s plus pn. So here we have two quantities, G of s into H of s and F of s. See, you can make a comparison between this G of s into H of s and F of s. You can see that the denominator of G of s into H of s and the denominator of this quantity, that is F of s, are same. Okay. So in order to predict the stability, we will have to make a look at the roots of the characteristic equation. So the roots of the characteristic equations, if any of the roots or any of the poles of the closed loop transfer function lies on the right half of this S plane, then it will indicate an unstable system, right? That we have studied in the root locus session or in the root Hurwitz criteria, right? So the stability of the system, so for the stability of the system, the roots of the characteristic equation should not lie on the right half of the S plane. See, here, in order to investigate the presence of the poles, actually the roots means it is a denominator polynomial or it is a poles. In order to investigate the presence of poles of G of s into H of s on the right half of the S plane, a contour C is chosen. See, a contour C is chosen such that it encloses the entire right half of the S plane. So actually this is the Nyquist criteria procedure. So if we have different functions such as G of s into H of s and also F of s, which is 1 plus G of s into H of s, in order to predict this stability, we have to take the characteristic equation and we have to check whether there are any poles lying on the right half of the S plane or any roots lying on the right half of the S plane. So in the Nyquist criteria, we will make the procedure like this. So in order to investigate the presence of poles of G of s and H of s on the right half of the S plane, we will assume a contour C. And that contour is chosen such that it encloses the entire right half of the S plane as shown in the figure. See, actually this is a contour C. See, it starts from here, right? It starts from here and it goes like this. And we are making an assumption that this contour, actually it looks like a semicircle, right? And this encloses the complete right half of the S plane. See, that is why it is given that R tends to infinity. So it encloses the entire right half of the S-plane. So we will take the contour like that, and such a contour C is called the Nyquist contour. So this contour is called the Nyquist contour, and the Nyquist contour is directed clockwise and comprises of 3 segments. See, you can see here that it comes in the clockwise manner, right? Arrow mark is in that manner, and it comprises of 3 components that is marked here, that is C1, C2 and C3. C1 starts from C1 is an infinity segment, and it goes along the imaginary axis. Also it goes along the positive imaginary axis, right? That actually this contour is plotted in the S plane, that is sigma j omega plane, and it starts from the, and this C1 starts from 0 to omega varies from 0 to infinity. Similarly, the second section of this contour is C2. Actually it is an arc of infinity radius, and it encloses the entire right half of the S plane, right? This encloses the entire right half of the S plane. And next, third is an infinity line segment, that is C3, and which goes along the negative imaginary axis, and in this case omega varies from minus infinity to 0. So along C1 we can write S will varies, we can make a substitution, S is equal to j omega, with omega varying from 0 to infinity. That you can see omega varies from 0 to infinity, and S is equal to j omega. Similarly, along C2 you can write C2 is like a curvature path, so we can write along C2 S value will be, S is equal to limit r tends to infinity r into e raised to j theta, for theta varying from plus pi by 2 to minus pi by 2. So along the C2 semicircle path, limit r tends to infinity r into e raised to j theta is the equation. Theta varies from pi by 2 to minus pi by 2. Similarly, along C3 we can make a substitution, S is equal to j omega, and in this case, in the case of this contour, we can see here the omega will vary from 0 to minus infinity, or minus infinity to 0. And using the loop transfer function g of s and h of s, the Nyquist criteria contour C is a S plane. Nyquist contour C is in the S plane and is mapped to g of s and h of s plane. And the loop and the mapped contour in the g of s into h of s plane is called g of s h of s contour. So actually in the Nyquist criteria we are mapping it to g of s into h of s plane. The S plane is a complex plane. Any point on the complex plane can be expressed by the complex number in polar form r into e raised to j theta, and r is the magnitude of the magnitude and theta is the argument. Now we can predict, or we can define the Nyquist stability criteria. So if the g of s into h of s contour in the g of s into h of s plane corresponds to Nyquist contour in the S plane that encircles a point minus 1 plus 0 j in the anti-clockwise direction as so many times as the number of right half S plane poles of g of s into h of s, then the closed loop system is stable. So Nyquist criteria for the stability is stated like this, that is if the g of s into h of s contour in the g of s into h of s plane corresponding to Nyquist contour in the S plane that encircles the point minus 1 plus 0 j in the anti-clockwise direction as many times as the number of right half of the S plane poles of g of s into h of s, then the closed loop system is called stable. So that is the definition of the Nyquist criteria stability. So in examining the stability of the linear control systems using the Nyquist stability criteria, we come across the following 3 situations. First one is no encirclement, second one is anti-clockwise encirclement, third one is clockwise encirclement. In the case of no encirclement of minus 1 plus 0 j point, this implies that the system is stable if no post of s of s into g of s comes in the right half of the S plane. If there are poles on the right half of the S plane, then the system is unstable. That we have studied in the previous classes. That means if there is a pole in the right half of the S plane, then the system will be unstable. So in the case of Nyquist criteria, if there is no encirclement of minus 1 plus 0j point, this implies that the system is stable if there are no poles of g of s and h of s in the right half of the S-plane, provided that there should not be any pole in the right half of the S-plane. So second condition is that anti-clockwise encirclement of minus 1 plus 0j point. In this case, the system is stable if the number of anti-clockwise encirclements is the same as the number of poles of g of s into h of s in the right half of the S-plane. If the number of anti-clockwise encirclements is equal to the number of poles on the right half of the S-plane, then the system will be unstable. And third case is clockwise encirclement of minus 1 plus 0j. And in this case, the system is always unstable. Also in this case, if no poles of g of s into h of s is right-handed, if no poles of g of s and h of s is right half S-plane, then the number of clockwise encirclement is equal to the number of poles of closed loop system on right half of S-plane. So these are the three conditions and relating to the stability, and we will see the session more detail when doing problems. That's all about this topic. Thank you.